This is a GCSE AQA chemistry question. It's from Trilogy paper, and this is a higher question. And in this one, we're going to look at bonding and exothermic and endothermic reactions. I'm going to recommend you pause the video, have a go as you work through, and then review later. So let's take a look at each section. Here is part A and B, part C, and finally part D. So this is an 8-mark question. So let's go back and take a look. We have got here, label the activation energy on figure 1. Now we have got to remember that the activation energy is the hump you've got to get over. It's the energy that you need to put in to ensure a reaction can take place. We can also talk about it in the context of collision theory, but in an energy profile diagram, which we can see over here, it's going to be from the energy of the reactants up to the top of that peak. And you'll notice I've been very careful with a line going across to show it's at the same height, and my arrowhead has gone right to the top. Very often people can do a very rough arrow, and the problem with that is it doesn't go all the way to the top. So do be careful to draw those carefully, preferably with a ruler. We are then asked to determine the overall energy change for the reaction between hydrogen and oxygen, shown in part A. So I've already got the line here. I'm going to add another one, and I'm going to read carefully. The reactants have an energy of 800 kilojoules. The products, 300 kilojoules. We want to know what the energy change is. So to get from 800 to 300 is a difference of 500 kilojoules per mole. Technically, this is an exothermic reaction, so it's negative 500 kilojoules per mole, but either of those did get the mark. We're going to move on to covalent bonding. And in this, you are asked to complete the outer energy levels in a molecule of O2. So on this, there is a very simple route that you can take through. As the two atoms are the same, you can do it for one oxygen and then repeat it for the other. So oxygen is in group 6. This means it has 6 electrons in its outer shell. If it has 6 electrons in its outer shell, it means it wants to gain 2 more, and it will do that by forming 2 covalent bonds. So the oxygen on the left puts 2 electrons into the one shared area that exists between the 2 oxygens. The other oxygen will do exactly the same. So I can now see my 2 covalent bonds. All that's then left is to put the remaining electrons on. They won't be in shared areas. Oxygen is in group 6. 2 of them have been used. That means there are 4 remaining that are not part of covalent bonds. So I put 4 more on each oxygen. Let's just double check it. This oxygen now has 2, 4, 6, 8 electrons. This oxygen has 2, 4, 6, 8 electrons. We're done. And finally, moving on to part D, we have a bond energy calculation. Calculate the overall energy change for the reaction. They've provided you with the equation showing all of the bonds, but be very, very mindful of the balancing. So first of all, let's deal with the bonds broken. We're breaking apart 2 hydrogen peroxide molecules. Within 2 of those, we've got 4 OH bonds. There's 2 OH bonds in each hydrogen peroxide. We've been given the value. That's 4 OHs, which is 4 463s, which is 1852. Bond breaking is an endothermic process, which means this is a positive value. I'm also breaking apart 2 OO, single bond O's. And so that's 2 times 138, that's plus 276 in total. And that means my total energy for bonds broken is plus 2128. Now I'm going to do the same thing with the bonds formed. I am forming 4 OH bonds. I've got 1, 2 in water, and I've got 2 moles of water. So that's 4 times negative 463, because making bonds is exothermic, so the value is negative 1852. You've also formed one O double bond O bond, and that's 1 times negative 496. So I've got negative 1852, negative 496, add them together. The total energy released when new bonds are formed is negative 2348. So I've now got the energy required to break the bonds, energy released when new bonds are made. I'm going to add these two numbers together, 2128 and negative 2348, giving me a value of negative 220 kilojoules. And that takes us to the end of the question.